saw some of the important characteristics of common emitter amplifier, and these included voltage gain, input and output resistances. In today's lecture, we look at another important characteristics, which is voltage swing. All right. So before we start our discussion related to common emitter amplifier, in general, when you see an amplifier like this and you have a load resistance connected, and of course we want to deliver power to the load, and for a given value of load resistance, obviously the power then depends on how much voltage you can build up at the output here. Okay, and therefore our interest is in power delivered to the load, and which translates for a given fixed value of load resistance, the amount of voltage that you can build up here. Okay, and therefore to deliver the maximum possible power, you would like to build up the maximum possible voltage swing here. All right, and another reason you can see here is that, and so as I said, you would like to build up V naught as high as possible, and of course the limits are that we would like V naught to reach as close as possible to the positive supply rail here, VCC, and similarly on the negative side, we would like V naught to reach as low as the negative power supply rail here. So when swing is of interest, we usually want what we call as a rail-to-rail output voltage swing. Rail means this is the positive supply rail and this is the negative supply rail, and we want V naught to get as close as possible to VCC and similarly as close as possible to VE here. Okay, so we want that, but voltage swing is not always important. Okay, take this particular case here. This is a multi-stage amplifier, and in this case we have shown a load resistance of 100 ohms, and obviously because there's a load resistance here, I would, power delivered to the load is important, and I would like a large swing here at this particular point in order to deliver maximum possible power here. So let's say my supply voltage is 5, and this is of course ground, so I would like a swing of 4 volts here at this point. Now this amplifier stage has a gain of 1. So which means that if I want a sinusoidal voltage with a 4 volt peak to peak, let's say amplitude here, then the voltage here would obviously be 4 volt here. Okay, which is fine, which says that swing is important here, and says swing is important for this amplifier also. Okay, but then this amplifier, it has a gain of 100, and therefore the swing that is required of the first stage is only 40 millivolt. 4 volt divided by 100 here. So note that when I have a multi-stage amplifier like this here, swing is important obviously for the last stage here. Swing may not be as important for your first stage here, because here all you require is 40 millivolts. Okay, so swing is important here, swing is also important here. Note the difference between these two amplifiers here. This amplifier also has to build a 4 volt swing. This one also has to build a 4 volt swing, but the difference is this one builds it across the load, which is usually small, often small here. So what it has to do is not only build up 4 volt peak to peak swing, but it also has to deliver current, significant amount of current, because as this 4 volt gets dropped across 100 ohms, there's a significant amount of current here. While this amplifier, it doesn't see the load directly, and often what would happen is this amplifier sees the input resistance here, and the input resistance would in general be much larger than the load resistance here. So this amplifier also has to develop 4 volt, but the difference is that it develops it across a much higher resistance, and the current requirement is much lower. So this can be a lot more tougher to do here, 4 volt swing, along with the large current that you require here, as compared to 4 volt swing here with little current that goes in here. Okay, so both are 4 volts, but then the requirements of current also matter here. 4 volt across, what kind of an element are you building? Okay, and it also emphasizes that, at the input stage, for example, if you have a multi-stage amplifier like this, at the input stage, you may not care much about the swing here. It's only 40 millivolts requirement here. Okay, so keep that in mind. So we'll go forward with the common emitter amplifier and see how much swing can my common emitter amplifier develop across the load, and what are the factors that restrict the swing here, and how do I design this particular amplifier to get the maximum possible swing here. Okay, so this is our amplifier, and let's understand this particular diagram here. Okay, this particular diagram is showing you the voltage at this particular point here, at the collector. Okay, and we note that voltage at the collector after passing through the capacitor, what it will do is filter out the DC and give you the sinusoidal voltage here. Okay, all right. So let's focus here. Before that, let's note there are a couple of voltages here. I know that my voltage at any point in a circuit like this will not exceed VCC here. So we've drawn one line here showing a limit, one limit here. So that's VCC. The other line that I've drawn here on the lower side is VE here. Note that VE is over here, this voltage. And of course, we have a DC voltage here. And because there is a capacitor connected to the ground, what it means is that for an AC, this is a short. And so no AC voltage will develop across this particular point. Okay. So this voltage is a constant and we can draw a line here, VE. Okay. It's a fixed voltage here. That's another limit here, which is VE here. And this shaded region here, the height of this shaded region is 0.2 volts, which is, we say, is the minimum VCE required to stay out of saturation region. Now remember, all these amplifiers will work properly if your transistor works in forward active mode. The moment your transistor goes into saturation region, the output gets distorted. Okay, so for that reason, we are saying we have drawn a band here indicating that as you enter into this particular band, the transistor would go into saturation region. Okay, all right, so that's VCC here and that's VE here. This voltage here, you know, because we have R1, R2, RC, RE, it has some DC value here, which we call as VCQ. Q means quiescent point or a DC point here. So we've drawn this particular line here. That's VCQ. So these are all decided by my biasing here, VCQ and VE. Now, when I apply a sinusoidal voltage here, this voltage will of course modify base emitter and the signal travels and I get a sinusoidal voltage here also. So on top of DC that you see here, I get a sinusoidal also. Okay. And the sinusoidal is what will travel to the output here. Okay. So if the output sinusoidal voltage has a amplitude of V0, I will get a sinusoidal voltage of amplitude V0 here as well. So now this is what is happening. This curve here now shows the total voltage at the collector, which is made up of a DC part here and a sinusoidal part here. Okay, so now this represents the net voltage here. And this height that you see here is the swing that will develop across the load here. As it passes through the capacitor, the DC part VCQ will go away and you are left with the sinusoidal part here. So we are interested in getting V0 that you see here as high as possible. And obviously, if I apply a sinusoid here, I want a pure sinusoid at the output. I don't want it to get distorted. The whole point of amplification is to build up the signal without changing its shape, without changing its, without distorting it. So we would like V0 here and we would like V0 here. So now the issue is how large a V0 can I get? So now note what happens here. This point is fixed. Okay, VE is fixed here. Now as my sinusoidal signal comes in, the net voltage at the collector rises. As it rises, what is the collector emitter voltage? It also increases. The net collector emitter voltage. Remember, net collector emitter voltage also rises here. That's the difference between here and here. Fine, then it comes back here. Then as it dips, what happens is the collector emitter voltage becomes smaller and smaller. Because note that the black curve that you see here is the net collector voltage. And emitter voltage is fixed. So what happens is effective collector emitter voltage becomes shorter, smaller and smaller. If you eventually if you keep on increasing this, what would happen is that this will touch this particular point. Now if you go beyond that, what would happen is effective collector emitter voltage will become less than 0.2 and your transistor is entered into saturation. And then the signal will get distorted. So this is telling us that the maximum, if I bias it here, the maximum value of V0 that I can get is VCQ minus VE minus 0.2, right? So what it says is that the maximum value of V0 that you see here has to be less than or equal to VCEQ minus 0.2. That's a limit, right? So this is the collector voltage here. This is the emitter voltage here. The net difference is VCEQ here minus this band here, which says that the transistor has entered into saturation. And so this is a limit on output voltage swing. I can't get a V0 here larger than VCEQ minus 0.2. That's one limit. Okay. And now obviously if you want a larger swing, what you would want is, if VE is fixed for you, then what you would like to do is take VC up and up and up, right? You would like to push it above. But then you can obviously see now, as you push it up and up, what may happen is the positive part will start touching the VCC here, and you can't go above VCC. Okay, so another limit will come from there. All right. So this is a limit on swing coming from the fact that my transistor should not enter into saturation. If it enters into saturation, then the signal gets clipped and I get distortion. Okay, so that's the limit here. V0, maximum value of V0 of the output here will always be less than VCEQ minus 0.2 here. And 0.2, of course, depends on the saturation voltage. It may be 0.3, as I said, 0.4 also depends on the transistor. So that's one limit. So if you want a particular swing, let's say a particular value of swing, let's say you're looking for 2 volt swing, then obviously it says you should bias your transistor in such a way that collector emitter voltage is larger than 2.2. You have to ensure that. So that's telling you how to choose a bias point. That all depends on how much swing do you want here. And how much swing do I want here? Well, that would be decided, let's say, by how much power, let's say, you want to deliver to the load. If you have a 1K load and you want to deliver, let's say, 1 milliwatt or 10 milliwatt or whatever, from there you will find out how large a V0 do you require. And how large a V0 will then determine how you bias your transistor. So depending on the amplifier's characteristics, you will find that you need to bias it at a particular point. Okay. All right. In this case, how large can the swing be? This is the amplifier that we had seen earlier, 10K here, 4K and all that. If you do the bias point analysis, you get 8 volt here, you get 5.3 here. And so this is the picture that you build. 8 here, 12 here, 5.3 here. And the swing that I will get is 8 minus 5.3 minus 0.2 is 2.5. That's all a swing that I get here. Okay, 2.5 volt swing here. So obviously 2.5 is much smaller than what my supply voltage indicates, 12 volts. So I would like to increase my swing. And now you can see this particular diagram and decide how can you increase the swing. What would you do? Well, maybe you can take this and push it up, right? Push it up. That's one way. The other thing is you also realize maybe we can take VE here and push it down, right? If I take VE here and push it down, how do I push VE down? By maybe reducing the emitter resistance and all that. Right? So those are the things that you'll do in order to increase the swing here. But let's look at the other limit here. All right. As I said, we need rail to rail swing here. So that's one limit that we have already seen, transistor going into saturation region. The other one is, suppose somebody biases the transistor such a way that VCQ is very high, large value is 11. Now, of course, on top of VCQ, again, I have a sinusoid. And now you can see that the maximum value of V0 that I can get is 12 minus 11 here, only 1 volt. Right? So there, now, so this one, where is this limit on swing coming from? That your net voltage cannot exceed VCC. Net voltage cannot exceed VCC. So this limit then that you see here is nothing but VCC minus VCQ. Okay? This is VCC here and this is minus VCQ. So what this diagram is showing is that your output swing will also be less than this value, will always be less than this value, okay? Which is nothing but ICQ-RC here. If you go back and look at your amplifier, VCC minus VCQ is nothing but the drop here collector, which is ICQ-RC. All right? So we have 2 limits here. Now, which one will determine my swing? Whichever one is smaller. Okay? If I bias it like this, obviously this condition will get violated earlier and my swing will be determined by this one here. If I bias it very close to my VE, this constraint will get violated and my swing will get determined by this condition here. So whichever one is smaller will determine my swing out of these 2. Okay. So now what would be a optimum bias point? What would you like to do? Maybe what you would like to do is, you know, if this, as we said, if this is very close here, then this is determining the swing. If the bias point is very close here, this is determining the swing. So obviously you would like to put the bias point somewhere in the middle. Okay, so that's what you would do here. What you do is, this is VCC here and this is VE here. So you situate the bias point right at this point such that on the positive side it starts touching the supply voltage rail here. On the negative side it starts entering here. And that's the maximum swing that you can get according to this simplified picture here. So these are the 2 limits. And to get the maximum possible swing from a diagram like this, what you would do is you would try and make both of these limits equal, right? So this is 12 and this is 5. So you would like to make the equal here. And if you ignore this 0.2 for a moment here, if you do want to do a little bit simplified analysis, what you would do is you would situate your bias point here in the middle, VCC plus VE by 2. So this is VCC point here, this is VE here, and you situate it right in the middle of these two here. If you want to be more accurate, you can write here VE minus 0.2 as well. Okay, so you can do a more accurate calculation. So for our amplifier then, if this is 12 and this is about 5, then we would like to situate it at 8.5 volt. Okay. And what is the maximum swing that I will get? Once I situate it like this VCQ, the maximum swing that I will get is VCQ minus VE, VCQ minus VE here, so which tells us VCC minus VE by 2. Alright, so whatever is the total gap between VCC and VE, you can get a swing which is half of that. Okay, so that's how you would try and bias your transistor in the middle of these two limits here to get the maximum possible swing here. Of course, as I said, what you would like to do is this VE point, you would like to push it as low as possible. Because as you push this VE point as low as possible here, your swing will become higher and higher. All right. So, but there's there are other issues also which are important. Swing is not the only thing, and we'll see how low you can push VE and what are the consequences. Okay. So back to our amplifier here. This amplifier then if I bias it at 5.3, then the I would like this particular point to be around 8.5 volt here. Okay. All right. So that's something that we've already seen here. So let me skip. Okay. So the issue is that if I want even larger swing, as you can see here, so we know how to bias it right in the middle of these 2 points here. If you want a larger swing, you would like to put VE, push it lower and lower here. All right. Can VE be made 0? Why did we put this RE? For bias point stability. Remember we had put that. So if as I reduce my value of RE or I reduce the drop, my bias point stability will begin to suffer. Okay, so that's the price that I will have to pay here. So we'll see in a minute how do you choose here. So let's take this particular example. Suppose I want an open circuit voltage gain, which is about 100 or larger. Output resistance is 1K, and I want a swing of 1 volt. Okay. So let's say these are the characteristics that I'm looking for. Now, how do I go ahead and design this amplifier? R1. So design means now R1, R2, RC, RE. All these values I have to find. Okay. And so first thing is R0 is given as 1K, and we know that the output resistance is nothing but equal to RC. Okay. So that allows us to choose RC as 1K here. This says gain should be greater than 100. We know the expressions of open circuit gain, which is ICQ-RC divided by VT. So it tells us, this one tells us that gain, open circuit gain is nothing but ICQ-RC divided by VT. So it is telling us that you should keep ICQ-RC larger than 100 into VT, larger than 2.6. So it's telling you the drop here should be larger than this value, 2.6 volt here. Alright, so that takes care of this particular constraint, and we've already taken care of this one. Now let's focus our attention on 1 volt here, 1 volt swing. So 1 volt swing tells us that ICQ-RC must be greater than the swing equal to 1 volt here. Remember, go back to this constraint and keep in mind, the two constraints are, the output swing is always less than ICQ-RC, which means that if you want a swing of 1 volt, you have to keep ICQ-RC larger than 1 volt. Okay, and the other constraint is from here. These are the two things that you need to keep in mind with regards to swing here. Okay, so that's what I'm doing here. So I'm saying ICQ-RC must be greater than 1 volt here from the swing consideration, but I already have a constraint. ICQ-RC is 2.6, so this doesn't really matter for me. The other one is VCEQ must be greater than the swing plus 0.2 here, so VCQ must be greater than 1.2. So that's the other constraint that is coming from here. Alright, so this doesn't matter, and these are the constraints here. So now the thing is, how do I proceed? It says VCQ should be greater than or equal to 1.2 to get a swing of 1 volt. and ICQRC must be greater than 2.6, and here. So now to start, what I've done is, and I'll show you in a minute, this is, it will appear rather arbitrary at this moment. I've chosen the DC drop from here to here as 2.6. As I said, right now it's arbitrary for you. Okay. So suppose I do choose this as 2.6, then this tells me that my VC here, if this is 2.6, VC must be 2.6 plus 1.2 here. So it must be 3.8. Okay. So it must be 3.8 here. And then if this is 3.8, then it's telling you is, this is 9. So it's telling you ICQRC drop is 5.2. And this is of course much larger than 2.6, which is okay. You know, my constraint is to give a gain greater than 100, and I can get ICQRC as large as 5.2, and therefore I can get a gain which is pretty large. The gain, remember, open circuit gain is ICQRC divided by VT. So I can get a gain which is 5.2 divided by 26 millivolt, which is as large as 200. Now, there are several things under my control. In this case, what I am doing is, the person who's asked me to design has said he was, suppose this was not equal to, but greater than or equal to. So here we have taken a choice that we are going to give a swing of 1 volt, and we'll try to build the gain to the maximum possible extent. ICQRC, we have chosen 5.2. What you could have also done is, you could have said, well, I'm going to give a gain of 100, and I'll try to give a swing which is as large as possible. Okay, so that way also you can design it. All right. So this shows you then how we arrive at our choice of ICQRC here. And note that once I have a value of RC, then I will get a value of ICQ, and therefore I have my bias point. At how should I bias my transistor? Well, now I have a value of ICQ from here, and I have a value of VCEQ here. And so these are the two things that are required to determine R1, R2, and the rest of the parameters here, and which we have already seen here. So ICQ is 5.2 milliamperes here. We've already made a choice of VE here, and therefore RE turns out to be 0.5K. And we've already seen how to design the bias circuitry here. We use the fact that RB must be much smaller than RE by beta here, and we go ahead and do all of this, which you have seen, and we get value of R2 and R1. Okay. And if we calculate, nothing is specified about input resistance. If we calculate, we get a value of so much. So you saw that what we did was, starting from a specification, gain, output resistance, and voltage swing, what we did was, looking at all the constraints here, all these constraints, we arrived at a value of ICQ and VCEQ. So depending on the amplifier specs, you determine what is a suitable bias point. Where should I place my ICQ? Where should I place my VCQ? In order to obtain these kinds of characteristics. Once you have that, then we've already discussed, you have a method of finding out what are the appropriate values of R1 and R2, and those values to figure out, to complete the design here. But one point is rather arbitrary here, which is, we selected it to be 2.6. Okay. And so now let's look at, how do I choose my VE here? How small can VE be here? So from the point of view of swing, we would like this to go as low as possible. Okay, so let's look at that here. VE is ICQ times RE. That's the DC drop. Now, note what I'm writing this as VE is. I've written VE as RB, VT by ICQ into beta, into RE by RB by beta into VT. I've added some factors, divided it by some factors, multiplied by the same factor. You can see that they all cancel each other. RB by beta cancel each other. VT cancels each other. So it's nothing but the same VE drop. So deliberately written it as product of two factors here. Okay. Now, VE, then I can write it as RB, and VT by ICQ into beta is nothing but R pi. Okay. And this I can rewrite it as beta RE by RB into VT. All right. Now we see, can you see the importance of the two factors? How do you, so our goal is, how do I choose my VE? What does it affect? Well, we now see what it affects is. Sensitivity of my current to beta, we've already seen is given by 1 plus RE beta by RB. So what would I like? I would like my beta RE to be much larger than RB. Note here, look at this particular point. Sensitivity to beta is given by this expression here. So you would like beta RE by RB to be large. Now it all depends on how insensitive do you want to make. And you can see the price. The more insensitive that you want to make, the larger this factor will be, and the more VE is going to be. All right. So the issue is how large or small. It all depends on how insensitive do you want to make. That's one point. What about this point here? If we look at this one, this is RB by R pi here. And we know that input resistance when I look from here is RB parallel R pi. So I want this factor to be large, because if RB is not large here, then what it will do is it will start pulling my input resistance down. It will start pulling my input resistance down. And as I said, we would like to keep RB 10 times or more larger than R pi, so that my input resistance then is limited by R pi and not RB. So you can see the effects of these two terms here. And VT, of course, is a constant for us. Okay. So now choice 1 and choice 2. These are the choices that as a designer you have to make. You have to decide now how large an RB should I keep here. Now how large an RB would depend on what is my specifications for Rn. In general, I would like to keep Rn as large as possible. So it depends on what the requirements of Rn are. And on that basis, you would like to keep a certain value of RB. And similarly, depending on the insensitivity to beta, you would like to keep this particular factor. So those are the choices that you have to make. And now the choice that I had made was, I kept this factor 10. I made RB 10 times R pi. And I made this factor beta Re 10 times RB. So sensitivity then becomes 1 plus 10, becomes something like 10%. And this is RB is 10 times R pi. So if I do 10 into 10 into VT, comes out to be 2.6 volt. So reasonable values that I had kept here of this one, and then I get 2.6. Now, you could reduce it to 1 volt, and it all depends on how you reduce it to 1 volt. Maybe you reduce this factor, or maybe you reduce this factor. And you'll know what the price you have to pay for doing this. Okay, so that's how you choose VE. It tells you how you arrive at a value of VE and what are the choices that you have to make. And so you can see here, now if you want to increase the swing, we wanted VE to be dropped further down, and therefore swing will come at the expense of either compromising this, which is sensitivity to beta. Your circuit, the entire amplifier becomes more sensitive to variations, or it will come at this expense, then your amplifier's input resistance will go down. All right. So these are the two consequences that you see about the choice of VE. Okay. So on that basis, one can then select VE and then, go ahead and complete a design. Okay. The picture that I painted about voltage swing is a little bit simple here. Now let me illustrate why it is simple. All right. And I'll illustrate it with a little bit of simulation results here. So let's look at this amplifier. It's a simplified amplifier here. There's no RE. Okay. No RE here. It is biased from the base side in this particular manner here. Okay. So in this case, what happens is note that 5 volt battery is there. RC is 1K. We have 430, and we are applying signal from here, and then looking at the output here. And my load is, you can see, very, very large. It's like open circuit. Okay. Load is open circuit here. Now, what I've done is, for this choice of RC and RB, my transistor is biased at 4 volt here. You can see here, VCQ is 4 volt here. This line that you see is 4 volt. And VCC is 5. VCC is 5 here. So now it tells me, and if I calculate the gain for this amplifier is 36.6. Okay. Now, obviously, if this is 4 and this is 5, it's telling me that I can get a swing of 1 volt. 5 minus 4, 1 volt I can get. Now, how will I get a swing of 1 volt here? To get a swing of 1 volt, I have to apply a certain input voltage here. How much voltage should I apply? 1 divided by the gain, which is about 27 millivolt. So I should apply this much input voltage here. It will get multiplied by the gain, and I will get a swing of 1 volt here. Right? So suppose I go ahead and do that in my simulator. I apply this much and then look at what happens here. Okay, so this is what I'm expecting. That I will see a DC of 4, and then it will go up to almost to 5, and then it will come back to 3. Right? 5 here and 3 here. This is what I expect. Let's see what it gives. This is the output. DC value is 4 as usual, no problem. goes, what did I expect here? 3. What does it go to? Note the value here. 2.5. And what did I expect? It would go up almost to 5. And where does it go? 4.6. What do you note about this sinusoid here? What? Not just shifted. What do you see about this sinusoid here? What is the positive, negative swing? 4 minus 2.5, which is 1.5. And what is the positive swing? And what can you say about the this sinusoid? Distorted. Sinusoid has gotten totally distorted. Positive swing of only 0.6 and negative swing of 1.5. It's a totally distorted sinusoid. All right. So this was something that we totally neglected. When we talked about a swing, remember we said, well, if you bring it here, it can go up so much and go down so much here and all that. We never thought about distortion. That my transistor is actually nonlinear. And this is what is happening because of the nonlinearity here. I'm getting a swing of 0.6 here and 1.5 here. In fact, I'm not able to reach 5 volt here. I could only reach 4.6. Now you may say, well, why don't you drive the amplifier even harder? Apply even larger input. It's not going to happen. Okay. Even if I apply even larger here, this is not going to go to 5 volt here. Okay. So what you're finding is then, can I say, what kind of a swing do I have in the amplifier now? How much swing do I have? Do I have 1.5 swing or do I have 0.6 here? I mean, difficult to say what you have, right? Because the sinusoid is also. So you are saying that when you say I have a swing of 0.6 volt, you also have to specify how much distortion do you have. Because always in your output signal, there will be distortion. And there's no meaning in saying I have a swing of 1 volt. You also have to say the following. I have a swing of 1 volt with so much harmonic distortion. Then that's a complete sentence. Because two people can say, well, I have a swing of, for example, here we can say peak to peak voltage is 2.1. So you can say, well, I have a peak to peak swing of 2.1 volt. Right? Another person says, I also have a peak swing of 2.1 volt, and the two can differ a lot. This can be 2.1 volt peak to peak with, let's say, 10% or 50% harmonic distortion. Another one can be 2.1 volt peak to peak with 1% harmonic distortion. And these are two very, very different things. All right. So the saying what is the swing is incomplete. You also have to say how much harmonic distortion are you getting. Okay. So that's important. Now, so I showed you that I'm not able to reach this limit here, 5 volt here. Now you must be wondering, can I ever reach the negative side here? All right. Now, two things you see here. The positive, we were expecting 1, and it's actually much less than 1. Negative also, we were expecting 1. It's actually more than 1. On the negative side, you get more voltage. All right. On the positive side, you get less voltage. So, can it touch the negative supply? I mean, negative, can it touch this particular point here? Let's see. So now what I did was, I rebiased my transistor and I made this as 1 volt here. By adjusting the resistance here, I made it 1 volt here. Now what should happen is, this is 1 and my VE is 0. And therefore I should get a swing of around 1 minus 0, which is 1 volt, minus this drop here, 0.2. So I should get about 0.8 or so. So what I'm doing is I should get a swing of around 1. 1 divided by AV0 is 7.2 millivolts. So I'm applying that. Do I get that? Well, it does touch here. So I can go right down to this particular limit here. Okay, so that it does. But this one, it doesn't touch here. Okay, and here also, note, it's always there. Positive swing is 0.62 and negative swing is 0.8. Positive swing, you will always get a little less than the negative swing. And how much is the difference between the two is an indication of how distorted your sinusoid is. The more the difference between these two, the more distorted your sinusoid is. Okay? Now, we also said that in this case, the best bias point would be that you bias it in the middle, right? So let's do that. Let's look at a case here where what I did was I biased in the middle. My bias point was 2.5. 2.5, and one limit is 5, the other limit is 0. So I would have expected to go to 2.5 here and minus 2.5 here, right? So I expect a swing of 2.5. And what do I get? Well, on the negative side, it starts touching here, 2.2, which is okay. On the positive side is only 1.1. It's not going. I biased it in the middle. This is 0, this is 5, and we biased it at 2.5. And the swing that I get is only 1.1 in the positive and 2.2 in the negative. So I'm not getting the swing that I want. And what is causing this problem is distortion. Distortion is causing problem here, and we are not getting the swing that we want. We wanted this particular point to be close to here. It's not going there. And so therefore we have to understand, why is this distortion coming? Where is it coming from? How do I quantify it? As I said, swing without specifying how much distortion you get is incomplete. You have to say how much distortion you're getting at the swing that you're talking about. Okay. So let's look at then, where is the distortion coming from? So this is the picture that we had painted about our amplifier. Our amplifier works in 3 steps. The input voltage that you apply, it changes the base emitter voltage. Base emitter voltage translates into a certain current. And the current flows through some collector and load resistance and develops the voltage here. Which is the nonlinear part? See, this goes to VB, that's not a problem. The signal appears across your base emitter. This is a nonlinear relationship, which we are approximating by a linear relationship. And that's where all the trouble comes here. Okay, this is the trouble point here. Once you have a signal, the signal flows across a load. This is a linear resistor. So there's no problem in here. There's no problem in here. The problem is this part here. This is where the transistor action is there. You change the base emitter voltage, the collector current changes. And that's where all the distortion is coming. Okay, so let's look at this particular part in detail here. We know that collector current is actually an exponential function of base emitter voltage. We've said that. Now here, what I've written is the total collector current is equal to the bias value plus a sinusoidal value IC. IC is the incremental value here. Where is this IC coming from? I have an incremental VBE here. And this is the bias point here. Alright, so this equation is what I have. VBE is what? VBE is nothing but coming from here, signal here. So that's the sinusoidal part, and this is the sinusoidal part of the current here. So my interest is in sinusoidal current because I'm interested in sinusoidal voltage here. So let's calculate IC. This small IC that you can see here, I can write it as, note that the first term, IS exponent VB by VT is nothing but the DC value of the current. That's the DC value of the current, because if you don't apply any sinusoid here, this goes 0, and you get a normal sinusoid, normal DC current here. So the first part, IS exponent VBEQ by VT is nothing but ICQ. So I can write here, sinusoidal IC is equal to ICQ, exponent VB by VT and minus ICQ. So this is sinusoidal, and this is sinusoidal. So that's the actual relationship. And what am I approximating it by? I'm saying IC is equal to GMVB, a linear relationship. Okay. And that's where the trouble is. The relationship between IC and VBE is a nonlinear relationship. Okay. Now, let's say my input is sinusoidal, and input is same as base emitter voltage here. It goes there. So Vs equal to VBE. This is the amplitude and sine omega t. Alright. So Vs equal to VBE0 sine omega t here. So what I'm going to do is take this term, put it here. Alright. So I'll put it here and define, let's say VB0 by VT equal to M here. If I do that now, note that ICQ I can take it out. Okay. So IC by ICQ will be equal to exponent M sine omega t minus 1 here. What is M? VBE is nothing but VB0 by VT is M here. So I get M sine omega t minus 1. Okay. So what it says is your sinusoidal current, collector current, goes like this here. Okay. And what we have been doing is the exponential we have been approximating as M sine omega t. We have been approximating as M sine omega t and saying this is also sinusoidal. If this is sinusoidal here, we are saying the collector current is also sinusoidal, but it's not. It's actually exponent of a sinusoid. And therefore, if we expand it, what we'll get is sine omega t plus sine square omega t plus sine cube omega t, and you'll get all the higher harmonics. Okay. So let me show you how this changes here. And the important parameter is M. Note here. What is the magnitude of the sinusoid divided by Vt? M is an important parameter. If M is very small, then you can see here IC will be almost like a pure sinusoid, because the exponential becomes, you expand the exponential and you get only the first term. So M, this is the most important parameter here. It tells you how nonlinear is your IC. So let me show you a couple of graphs here. Look at this one. What am I plotting? IC is the sinusoidal IC, normalized by the bias current here. And this, the black one is what I get from the ideal value. Ideal value meaning GM times VBE. That's the ideal value. This is what my ideal value is, or my small signal approximation gets. The red one shows you the actual IC that you get here. So the black one is the ideal sinusoid, and the red one shows you the distorted sinusoid. So the effect is, you note that on the positive side you get more current, and on the negative side you get slightly lesser current here. And this is for a case where M is equal to 0.2, which means what? The sinusoidal amplitude divided by Vt is 0.2 here. And I can calculate, now this red one shows me a distorted sinusoid, and I can calculate the distortion, and I'm telling you the distortion is 5%. We'll just see in a minute, okay, how to calculate distortion. Distortion is 5%. 5% distortion, harmonic distortion, second harmonic distortion. Because you can see here, the red one is not a pure sinusoid. Positive amplitude is more than the negative amplitude. So I can break it up into harmonics, and the second harmonic divided by the first harmonic is 5%. Okay, so 5% distortion for VB0 by Vt equal to 0.2. Suppose I now increase it to here, M equal to 0.4. Now note, M equal to 0.4 means the sinusoidal amplitude has increased. And then this goes like this, and this goes here. And the distortion is 10%. Sinusoid is 10% distorted. VB0 by Vt equal to 0.4 here. Then I put M equal to 1. I'm applying a sinusoidal voltage as large as the thermal voltage here. This is black one as usual is the ideal, and the red one is the distorted one. Distortion is as high as 25%. So the larger the input voltage that you apply here, the more the distortion that you will get here. Now can you see why my swing in the positive direction was less than the swing in the negative direction? You see this point, this current, when current increases, note that the voltage decreases in your amplifier. As collector current increases, the voltage decreases. So positive swing in the collector current translates into negative swing in the voltage. And negative swing in the collector current translates into positive swing in the voltage here. Because voltage is nothing but VCC minus IC times RC here. So that's where the negative part comes. So you are saying that because of the nonlinearity, the collector current, sinusoidal collector current itself is distorted. And if this distorted current flows through my RC or RL, obviously it will build up a distorted sinusoid. Alright, so I will get a distorted output voltage here. How distorted will it be? It depends on how large an input voltage do I apply. And you know that output voltage is related to input voltage through gain. So how do you get a large output voltage? You will have to apply a large input voltage. And if you apply a large input voltage, what do you get? Larger distortion. Alright, so as you increase the output voltage swing, the distortion will keep on increasing. So that's a natural consequence you cannot avoid because of the nature of the amplifier that we have. Okay, so let me calculate for you the distortion then. IC by ICQ. Now go back into this expression here. We had IC by ICQ exponent M sin omega t minus 1. So I'm just expanding it. M sin omega t plus M sin omega t square by 2 plus and so on and so forth. I'll not bother about higher order terms. Let's just look at the second harmonic distortion. Second harmonic distortion, sine square omega t is nothing but cos 2 omega t here. And its amplitude would be M square by 4. So second harmonic's amplitude would be M square by 4. And this is only M. And therefore harmonic distortion, M square by 4 divided by M is M by 4. That's the harmonic distortion. And M is nothing but VB0 by 4 Vt. So it tells us how much is the second harmonic distortion. It's related to how large input amplitude you apply here. Now we know that the output voltage is equal to gain times the input voltage here. Remember, this is nothing but input voltage here. So output voltage is AV times the input voltage here. And therefore, output voltage I can write as AV times this value here, and we get output voltage will be less than or equal to this value. All right. So here, what we are saying is, suppose you are interested in a harmonic distortion which is less than 5%. So if this term has to be less than 5%, it would tell you that this has to be less than a certain value. If this has to be less than a certain value, it will tell you is your swing will be less than a certain value here. So that's how we arrive at an expression for swing here, which is determined by how much harmonic distortion you can tolerate. If your application is such that you can tolerate harmonic distortion of 1%, well, you have to put 1% here, 4 VT, and whatever is the gain, and that will tell you how much swing will you get. If your application can tolerate 10%, then obviously you can have larger swing. So now we have gotten another expression for swing, which is determined by distortion. Earlier, we had not taken distortion into account, but now we are saying this is also important for us. Okay. So we'll stop with this particular graph here. So you can see now what are the limits. When we didn't talk about distortion, we said that my output voltage must be less than this. My output voltage must be less than this here. Now we are saying my output voltage must be less than this also. Where is this coming from? From distortion angle. Now if you compare these two, just compare these two. Which one is larger? I've expanded this one, 4 VT, AV into HD2. AV I've expanded, which is ICQ RC parallel RL by VT into HD2 here. If I look at open circuit voltage swing here, RL I neglect here. This gives me ICQ RC into 4 HD. So compare this term, which is coming from here, versus this term. Which term do you think will be important? Normally, harmonic distortion, we would like to keep it low. 1%, 2%, 5% here. Which means what? 4 HD that you see here, this term will always be less than this value. Alright? Will always be less than this value. And unless you talk about harmonic distortion, which is as large as 25%, when this becomes 0.25. So 4 into 0.25, then it will become like this. Alright, so most of the time what happens is, this is not important, this is the real constraint. VOM is ICQ RC into 4 HD2. That's the real constraint here, this is not important. Even before you reach this particular point here, where this point starts touching this swing here, your distortion has become so high that your output signal is not useful anymore. Okay, so this is not a limit here. You should go back and revise this particular limit as this one. Alright, what about this one? Is this still important? This I compared these two and said this is no longer important because this one subsumes this one here. Okay, it includes within it this particular one. In fact, this one can be looked upon as a special case where harmonic distortion is 25% or 0.25. So this is a special case here. Okay, so this is more general. What about this one? Should I bother about the first one? Because what happens is, this is only talking about coming about due to transistor nonlinearity. Now, if you don't take into account, what will happen is, if you push your VC into this region here, what will happen to the negative part? It starts clipping. It starts clipping, and then the signal gets very, very distorted. So this part remains. I have to keep my VOM less than this particular value here, because otherwise this signal, the negative part will get totally clipped, and my harmonic distortion would be even higher, much higher than what this will indicate here. Okay, because of the clipping, the sinusoid is totally distorted, and therefore this one, this one. So now these are the two limits then. VOM is VCQ minus 0.2, and VOM is less than this particular value. And from these two, then we determine now whichever one is lower will determine your swing. If this one is lower, then this will determine the swing. If this one is lower, this one will determine the swing. Now, for making this one higher, what should you do? HD2 is fixed for you. How do you make VOM larger? You make AV large. How do you make AV large? What is AV? Note here. So you make ICQ RC large. So as you make your ICQ RC large, what happens? What happens to VCQ? It goes down. So as you keep on making ICQRC large, this VCQ eventually comes down, and then this becomes more important. So what will be the ideal way of biasing? I will look at these two constraints now, and from there derive a way of biasing such that I get the maximum possible swing. Earlier I was looking at this and this to derive at the optimum biasing. Now I will look at this one and this one to arrive at the optimum biasing. Okay, so that's what we do here. This is one constraint and this is the other constraint, and the minimum of these two determines here. Okay, so let's come back to the example that we were discussing earlier. For this particular amplifier where R1, R2 are 10K here, RC is 4K. We had looked at this particular example earlier, and we had seen that the collector voltage is 8 volts here and this emitter voltage was 5.3. So now let's estimate the voltage swing here. So the first constraint is VOM less than VCQ minus 0.2. So if we plug in the values, we get 2.5 volt here. The other constraint on VOM comes from harmonic distortion. So ICQRC parallel RL here, HD2 by 25 here. And if we assume RL infinity open circuit condition here, so this translates into plug in the values of ICQ and RC here. So it's 4 by 25 into HD2% here. So swing, this tells us that the swing depends on how much harmonic distortion we are willing to tolerate. And so we get different values for different values of HD2 here. If we put in 5%, we get a swing which is 0.8 volts here. If we get 10%, it predicts 1.6 here. And for 15%, it predicts 2.4. In all of these cases, the constraint on swing is lower, or the prediction of voltage swing is lower as compared to this one. So my harmonic distortion is going to determine my swing here. 0.8 for 5% distortion, 1.6 for 10% distortion here. All right, so this is more important in determining swing rather than this particular value here. Okay, so let's next look at how do we bias the transistor in order to obtain maximum voltage swing here. So again, these are the two constraints that we have. And as we said earlier, if you make the collector voltage very high, then this becomes a limit. If you make the collector voltage too low, then this becomes a limit here. And for maximum voltage swing, we have to equate these two limits. So we do that, and after a little bit of algebra, we get the following constraint. We find that for maximum voltage swing, we should bias it in such a way that ICQRC is equal to this expression over here, which of course depend on the harmonic distortion that we are willing to accept. And once we have ICQRC here, one can also obtain a constraint on VCEQ. So that's how we choose these values here, biasing ICQRC and VCQ in order to obtain maximum voltage swing. And the swing that we can obtain is given over here. So VOM is equal to VCC minus VE minus 0.2 and the expression here. So this expression basically comes by taking, let's say, a VCQ that you have here and putting it in this expression, or ICQRC that you have and putting it in this expression. Each one of them will give you the same value of swing here, because for maximum voltage swing, both the constraints give us the same value here. So this is the final expression for voltage swing that we obtain, and this expression then takes into account the harmonic distortion here. Note that if I take harmonic distortion equal to 25% with a high value here, so this becomes 1 here, and if I take RL equal to infinity, open circuit condition, then this whole factor becomes 1 plus 1 here, 2, and then we are talking about maximum voltage swing, which is equal to VCC minus VE divided by 2. So we recover back our earlier simplified expression. So let's stop here, and next lecture we'll look at frequency response.